carriers will be towards the drain terminal, D terminal. So the entire conduction is started off because of the MOSFET that is sitting at the back end of the device. So if you look at the overall working of the device, the turning on happens because of MOSFET. So it is a voltage driven device. The moment I rob that positive voltage or I remove the positive voltage from the gate, the channel will be closed. If the channel is closed, we will not have any more base drive also available for the transistor that is sitting on the top. So the transistor also goes off and you are going to have the turning off of the MOSFET as well. Both of them are turned off one after another. First, you are going to have the MOSFET turned off, because of which the transistor will not have any possibility of getting further base drive. So the transistor will also go off. But definitely the time taken will be more than the MOSFET's turn off time, because you have the transistor already conducting. It is probably driven into saturation already. So it is going to take a while for the charge carriers to recombine. First the MOSFET current has to go to 0 and then only the base drive will go to 0 for the transistor. So you are going to have definitely more amount of time taken by the device for turning off even after the gate pulse is removed. So generally IGBT is called as a voltage driven device with a higher turn off time than the MOSFET. But because of the transistor mainly driving the major portion of the current, because MOSFET essentially plays a role in turning on and turning off the device. It doesn't really play a role in the overall conduction, because of which we are not going to have a large on-state resistance in this device. So the on-state resistance generally comes down in this particular device. So on-state resistance is less than MOSFET. But however, because I have a drift region, I also have a small channel, you cannot expect it to be as low as transistor. So on-state resistance of IGBT will be slightly higher than BJTs. So it is somewhere in between. It will not be, as low as BJT or as high as MOSFET. But because of the fact that I have so many layers here, we would be able to make it for larger rating. And not only that, because it's a voltage driven device and it is advantageous in every way compared to either MOSFET or BJT, a lot of research is going on in this particular device and the ratings have increased tremendously in the last few years. So the ratings that are available as of now are close to 5 kilovolts. And corresponding to 5 kilovolts, we have easily 1.5 kiloampere. But if we try to come for lower values of voltage, that is, let us say 2 or 2.5 kilovolts, we can easily get 3 kiloamperes and so on. So if you lower the voltage, you can go for a higher current, because heat sink design is a big problem generally. So we have at least of the order of 6 megawatt handling capacity quite easily in many of the IGBTs. Single-handedly they can handle 6 megawatt, and as the research progresses, in all probability we may get higher and higher rating possible. Okay. So if we look at now the spectrum of devices, right, and what is the kind of applications each of them have, right? So let me write the power on this side and let me write the frequency of operation on this side. So maybe I can say this is megahertz. Somewhere here let me write kilohertz, and somewhere here hertz. Right? And similarly, let me write maybe hundreds of megawatt. Maybe I should say hundreds of kilowatt. This is just a few kilowatt. Right? So, if I look at the intersection of a few kilowatts and megahertz, this is where generally we are going to have MOSFETs being employed. Right? And if I try to look at hundreds of megawatt and few hertz, maybe 50, 60 hertz, maximum 600, 700 hertz. That is where thyristors are employed. Right? If I try to look at a little less than hundreds of megawatt, somewhere here, and a slightly higher frequency, I should say at this region approximately GTOs are used. Gate turn of thyristors can be used for slightly higher frequency than thyristors, but they can also be used at little lower power level. But if I am talking about close to a few megawatts and few tens of kilohertz, around this region is IGBT. So IGBTs are used in roughly those regions. Whereas if I am talking about even lesser power rating than that, somewhere, right, and probably even slightly higher frequency or similar frequencies, somewhere here are BJTs. IGBTs can still handle higher power than BJT because more research has gone on and more improvements have come about. It's not probably the inherent property as such, but people have not put in effort basically for BJT. To be specific in terms of applications, yeah, almost similar. Frequencies are almost similar, but power levels are a little lower. Almost similar frequency. Typical applications, MOSFETs are used in all inverters, household inverters, UPS, right? Some SMPS, all the power supplies. Wherever we use, small capacity power supplies, most of them are MOSFETs. And MOSFETs are freely available in the market and it's not as expensive. IGBTs are expensive, more expensive, right? And BJTs, medium kilowatt drives. Industrial drives which may be of medium kilowatt capacity. Most of them might use BJT, but now most of them are being replaced by IGBTs. Invariably, they have been replaced by IGBT in many of them. So, these again, you can say static VAR compensator, we will see what it is at the end, where we are going to probably make sure that reactive power is supplied. We can put capacitor to supply reactive power. All of you have realized that power factor can be improved by employing a capacitor, right? Instead of employing a capacitor which will give me fixed amount of reactive power, can I employ an inverter and I can place the current as I feel like. The current can be put in lagging region, leading region, whichever region I want by appropriately gating the devices or firing the devices. So that is known as static VAR compensator, reactive power compensator. So I can compensate for both lagging as well as leading reactive power. Capacitor can compensate only for lagging reactive power. It can only provide leading reactive power. Whereas this can compensate for both lagging as well as leading reactive power. So static war compensators, wherever it is used, generally it is IGBT. And again, industrial drives, many of the industrial drives. Then induction heating system. You guys have seen induction cooktop, but that is all of 1 kilowatt or a few kilowatt capacity. Whereas when we use it in industrial scale to melt some metal, right, in furnaces, in those cases, again, IGBTs are used invariably. When we want to control the temperature, it's always good to have a power electronic equipment. So because of which, we would be able to control effectively the voltage and current that goes into the furnace. That's the reason. GTOs generally are used in many of the wind energy and solar energy conversion systems. Solar, what we get is DC. We have to convert that into AC if we want to feed it to the grid. So if I am getting from solar certain voltage, I might like to boost it up. So I may use a DC to DC converter, step up converter, to step up the voltage from a particular value to a higher value. If I want to step it up, then I may use a GTO based DC-DC converter. Similarly, in wind energy, what we get will be a variable speed. We will not be able to get a fixed speed. So if I have a variable speed, what I get out of the AC generator will be a variable frequency AC. I can't feed it to the grid directly. I want 50 Hertz. So I'll convert that into DC. So for AC to DC conversion, I can use GTO if I want, or I can again convert the DC into a higher voltage by using a boost converter. Depending upon the velocity of the wind, I'm going to have a particular frequency and particular voltage. If lower wind velocity is the one which is being faced by the wind turbine, then I will have lower voltage as well. So I might have to boost it up. So boost converters invariably are designed in these things using GTO, especially for boost conversion. Thyristors, you talk about very high capacity DC drives, maybe in steel rolling mills, right? Paper industries, if they use DC drives, generally thyristor controlled DC drives are used. HVDC transmission, what we talked about, right? And DC drives. These are major applications of thyristors. HVDC transmission generally cannot run without thyristor. It has been possible to have so many HVDC transmission systems all over the place only because of thyristors, right? Last but not the least, firing scheme for BJT / MOSFET / IGBT. Thyristor is a little different category of firing scheme it is having because of the fact that I don't have to give continuous pulses. If I give one pulse, it will be latched into conduction provided the current is greater than latching current, right? And it will stay in conduction zone unless I bring down the current below holding current and I reverse bias. So both conditions have to be satisfied. For turning on, I have to first of all have it forward biased, I have to give a gate pulse, and the current has to be greater than latching current. Only then it will stay in conduction state. For turning off, I have to make sure that the current goes below holding current and I reverse bias it. Only then it is going to go off. So thyristor need not be given continuous pulses. It can be just given one pulse and it will stay on. That's not a problem at all. That's why I could use a transformer for isolation. And the transformer was called a pulse transformer, and the pulse transformer was getting discontinuous DC. It was not giving, we were not giving continuous DC, rather we were giving discontinuous DC like this, high frequency ANDed pulses. That's what we were giving, right? Whereas I can't afford to do that for a BJT or MOSFET or IGBT. If I do that, the device will conduct during this time, it will not conduct here, it will again conduct here and so on. So I can't definitely do that. So I definitely need to isolate between the power and control or the gating circuit, no doubt, but I can't do it with a transformer. So how is the isolation provided? That is a major, discussion point for the firing circuit for any of these devices which require continuous pulses. So let us look at isolation. How to provide isolation? Most of the times, the isolation is provided using something called opto isolator or opto coupler. And this is all electronic portion. I am not even talking about power portion. We do everything electronic and then connect it to the gate and we are done with the electronic portion. The power portion is a completely a different circuit. Again, I have to connect it in a proper format and then I have to make sure that everything works there. Right? The grounds will be different. That's what I am trying to say. Right? So, let us say I have again a DC-DC converter itself, maybe with a transistor. I am showing a BJT. I am going to have probably a diode, freewheeling diode and a DC motor drive. And here is my power supply. Right? I might like to have actually this particular switch on only for maybe 40% of the duration, 60% of the duration it is going to be off and so on. Maybe I want lower speed. So that is why I am going to have the requirement of having only 40% of the voltage as compared to whatever is this VDC value. So this is 40% and this is 60%. Right? So which means I have to make sure that this device is on only for this 40% of duration. How I will generate this is a matter of detail, but I can probably give you one of the schemes. Normally what we do in analog electronic circuit based implementation is we try to get a sawtooth wave generated at this particular frequency. You can definitely generate a sawtooth wave with n number of analog electronic circuits that are available. If you just put in Google sawtooth generator, it will tell you, because CRO has a sawtooth generator within itself. So this is a sawtooth generator at a required frequency. Let us say I want to operate this transistor at 10 kilohertz. I'll get a sawtooth generator at 10 kilohertz. So I will basically make an oscillator kind of circuit at 10 kilohertz, which is generating sawtooth. Now I can put a comparator with op-amp. I can compare this sawtooth output with that of some constant DC voltage. DC voltage can be obtained from a regulator power supply. That's not a problem. So I can compare these two. Now what I am getting as the output of the comparator will be, wherever it is high, it will be actually giving me positive, provided I had given this to the positive terminal and I had given this to the negative terminal of the op-amp 741, for example. I can give positive terminal to the op-amps, this DC voltage to the positive terminal of the op-amp and this particular sawtooth to the negative terminal of the op-amp. So I have got clearly 40% on time and 60% off time. If I want to vary this, I have to just vary the level of this VDC, whatever I am giving from. Let me say VDC1, because this is VDC I have written. Okay. Or V control voltage, whatever. It will control basically how long it is going to be on and how long it is going to be off. Right. So now, let me show this in the form of a block diagram. I have a sawtooth generator. I have a DC control voltage. Both of them are fed to an op-amp comparator. So this is plus and this is minus. What I get from here obviously will be a waveform what we wanted, depending upon how much is plus VCC and minus VCC. Right? So I will get correspondingly this value. Now this I could have given directly to the transistor to turn it on, provided I didn't need an isolation. But I want an isolation. So I can't give this directly to the transistor. So what we use in between is something called an optocoupler. So in an optocoupler, internally there will be an LED. There will be an LED inside an optocoupler. And there will be a phototransistor on which this light will be falling at its gate. In the phototransistor's gate, so it is a small chip. Within the chip, there will be an LED and there will be a phototransistor, and exactly the LED's light that is being emitted will be focused on the base of the phototransistor. Right? So this will be connected to the ground, and I am going to have here this is connected to VCC. Okay? Now I will have definitely ground here as well. I will definitely have the ground for sawtooth generator, for the regulated voltage, everything. So if I call this as ground of electronics, whereas this will be connected to the power ground. This will be connected in all probability, or if I call one as ground 1, the other one is ground 2. The two are not connected together. Please understand, this optocoupler is coupled to the primary side and the secondary side are coupled to each other with the help of light. It is not connected through anything else. Electrically, they are not connected. They are connected only because of the light that is being emitted from the LED. So they are not conductively connected. No conductor connects both of them. So one side of the optocoupler is connected to the LED, that ground is different, whereas this ground, so if I may call this as ground 1, this becomes ground 2, another ground. So generally, in most of 99% of BJT, IGBT, MOSFET applications, we have to use optocouplers. Right? So this optocoupler essentially makes sure that the pulse is transmitted from one side to the other side without really having any electrical connectivity. So the grounds become completely isolated. Now whatever is available across this resistance will be exactly the same pulse. Right? So we should be able to get this, to our gate circuit wherever we want to transmit it finally. Right? So this portion is completely electronic, whereas we have to still work on the power portion, which we have not started as yet. Right? So much so for the pulse generation and pulse transmission in the case of maybe BJT or IGBT or MOSFET, and how the power ground and the actual electronic ground are isolated. So we will be starting on rectifiers. Let me at least give you a prelude as to how we are going to proceed today, and then we will be starting on the actual rectifier portion. Right? Until devices, whatever I taught is again my acquired knowledge. So I am really not good at device physics. So hopefully I am really coming to my forte from next class, because rectifiers and inverters, DC-DC converters, it is like the backside of my hand, because I have really repeatedly studied that. So I'm really glad I'm going to come to the rectifier portion. Okay. So let us see at least what all we are going to start off with. I think you will require circuit theory concepts very thoroughly for this. So if you guys have somewhat forgotten, I would request you earnestly to revise your circuit theory concepts to some extent, because we will be looking at RL circuit invariably, sometimes RC circuits, sometimes RLE, because battery charging, for example, is like RLE circuit, right? DC motor drive, for example, is like RLE, because EB, I will have back EMF. So you should know how RL circuits behave, how RLE circuits behave, how RC circuits behave, and whether I have R and C in parallel or R and C in series. So I want you guys to revise these portions, because we are going to superpose whatever you know in circuit theory along with devices. So it will be definitely more complex. That's the reason I want you guys to revise, right? And I'll be concentrating extensively in waveforms, quite a lot. Power electronics is nothing without waveform. So we need to draw waveforms. Like if I apply a sinusoidal voltage, how is the output voltage going to look like at every instant of time? What will be the voltage across the devices, right? All these things we'll have to look. So that's the reason we'll be concentrating on waveforms extensively, and I would like you guys to practice drawing waveforms for different circuits. So when we start, we'll first start with simple diode rectifier, that too half wave. Only one diode, not two diodes, right? If two diodes are there anti-parallel, then it will conduct all the time during forward biasing as well as reverse biasing. So we look at this, and this with R load, RL load. We'll start off with this first, right? Then we will go to the same rectifier, diode rectifier, maybe full wave, but we look at center tapped rectifier. Then we will go for full bridge rectifier. Then we will go for, all these are single phase, of course, first. All of them are single phase. So we are looking at single phase to DC conversion, single phase AC to DC conversion. Then we will look at thyristor or SCR rectifier. So in SCR rectifier, again we will be looking at fully controlled, that is 4 SCRs are used in a bridge. So this is known as fully controlled rectifier, right? So in fully controlled configuration, we will be looking at R load, RL load, RLE load, all three of them, right? And in this we'll have to derive the expressions, we'll have to look at the waveforms, we have to look at the different factors like power factor, how that is affected, right? And we would also see how the fundamental current is, fundamental voltages, that is 50 Hertz wala current and 50 Hertz wala voltage, and what is the displacement between them. All those things we'll look at. Then we will go for something called semi-controlled converter or semi-controlled rectifier. I use the terms converter and rectifier interchangeably. Okay, both of them mean basically AC to DC converters. So in this particular case, we will use 2 diodes and 2 SCRs. So they will behave differently compared to when we use only SCRs. They will behave differently. So we will have to look at them. Right? In this case also, we will at least see R load and RL load. Okay? I will definitely leave some of them as exercise to you so that you can draw the waveform. If you have difficulty, you can get back to me. You can try to do the simulation in a very, very simple software called PSIM. Okay? So PSIM, if you try to look at it, you know, you can simply put the components and see the waveforms very, very easily, even much simpler than MATLAB, Simulink MATLAB. So you guys will be introduced to PSIM and Simulink MATLAB in this particular course, for sure, if you have not been introduced already. Okay? Then we will go for 3-phase. Okay? So 3-phase AC to DC rectifier. So in this again, there will be fully controlled. You can start off with diode, then diode converters are uncontrolled. Then fully controlled is all 6 devices, because 3 phases, I will need 6 devices. All 6 devices will be SCRs, fully controlled. Then semi-controlled. So which means 3 diodes and 3 SCRs. So we look at all 3 configurations, that is uncontrolled, fully controlled and semi-controlled with all different loads. So we look at all these configurations, right? Okay. So I would request you to revise the circuit theory concepts thoroughly. Then we'll start off on the rectifiers in the next class. I'll try to, still I have not uploaded the problems, I do remember, but I'll upload some additional problems on all these devices, right?